Okay, there was a question about how to deal with uh, a sum of piecewise functions, I think, right? Where you were asked to maybe find the absolute maximum on an interval of something like this. Tell me if I'm getting this right. Something like that. Supposed to find the absolute extrema. Okay. So how do we do this? This is kind of an oddball problem. You don't see a lot of this kind of stuff. Piecewise functions are a bit of a pain. Or excuse me, absolute value functions are a bit of a pain because you have to write them as piecewise functions. And that just is, it's kind of cumbersome. I understand that. But, it's part of life in math anyway. So how do we do this? Well, we can take each of these absolute value functions and separately write those as piecewise functions. So the absolute value of x minus 3 written as a piecewise function would look like what? Keeping in mind that for absolute value functions, like the absolute value of a just equals a when a is positive, right? It equals the opposite of a when a is negative, and of course it just equals 0 when a is 0, right? Okay, so instead of a this time, we've got the quantity x minus 3. Okay, so it's going to equal just plain old x minus 3 whenever that's positive value. Now, when would that be? When is x minus 3 greater than 0? Good, okay. When x is greater than 3. Good. And then once you know what the cutoff point is, it's pretty easy to go from there. Then we know that when x is less than 3, then we're going to end up with the opposite of this, which is, negative x plus 3 or 3 minus x, whatever you want to call it. And then in the middle, when x actually equals 3, that's when this is 0, right? Okay, what about the absolute value of x plus 2? That's going to equal, good, x plus 2 when x is, it's greater than negative 2, good. When x is less than negative 2, it's negative x minus 2, and then in the middle, when x equals negative 2, it's 0. Okay, so then what does the sum of those two things look like? Well, we're literally just going to add up those two piecewise functions. Now, you got to think about this in terms of where are things changing, right? It's pretty boring. This top function is pretty boring when x is greater than 3. It's just that. But when x hits 3 is when it changes. Bottom function changes when x hits negative 2. So the sum of these two things is going to inherit both of those changes, right? So then, if we want to add this up, the absolute value of x minus 3 plus the absolute value of x minus 2, what is that going to equal? Did I just get that wrong? Plus 2, yeah. When x is, let's start from the left. What's the first change we run into is at negative 2. So when x is, I kind of give myself a lot of space here, didn't I? When x is less than negative 2, we're going to be there, right? We're going to be walking on this part of this piecewise function, this piece of the piecewise function. What about the top function? When x is less than negative 2, it's clearly less than 3, right? Does that make sense? So we're going to be here and here when x is less than negative 2. So it'll be a sum of those two things. We're going to get negative x minus 2 plus negative x plus 3. So we're going to get negative 2x plus 1. Does that look right? So that's what we get on this domain. Okay. Now we're gonna transition. Now we're going from negative numbers up towards positive numbers. We got to negative 2. Now when x is greater than negative 2, we're going to be, we're going to trip up to this guy, right? But as long as x is still less than 3, we're also staying there, aren't we? Right? Because that's easy to do. There are lots of numbers that are greater than -2 and less than 3. And when we're walking along that part of the domain, we're going to add up the two blue pieces, right? So we've got 3 minus x plus x plus 2. So the x's cancel. We just get 5. Right? Does that make sense? Okay, so on the domain where x is greater than -2 and less than 3, we're just 5. Okay. And then the other thing that can happen is if we keep moving to the right along the real line, we're going to get to a point where we come to 3, this boundary, and when x is greater than 3, we're going to be there and there, right? Because when x is greater than 3, it's obviously also greater than -2. So we'll add up the two green parts, and we'll get x minus 3 plus x plus 2, so 2x minus 1. Okay, does that make sense? And then at the boundaries, this thing would have, well, what would it be when it's actually, if we want to fill those in too, I guess. What about when x actually equals 3? What are we going to be? Well, when x equals 3, this is 0, and this guy down here is going to be 5, right? Does that make sense? If I plug in 3 here, when x equals 3, it's greater than -2, and so if I plug in 3 in the bottom function, I get 5. Okay, so we get that. And then if we go down here to the boundary and we say what happens when x actually equals -2, well, down here it's going to equal, when x equals -2, we get 0 for the value of this piecewise function. Up above, what are we going to get? If x equals -2, we're going to get 5, not surprisingly. Okay? Okay, make sense? So there's our piecewise function we get from the sum of those two things. Now, what if we differentiate? If we take the derivative of that piecewise function, real quick. Let's go ahead and just finish the problem. So if we take the derivative, let's just call this thing, how about, okay, it's f of x. So if I differentiate, now we're going to do f prime of x. What's the derivative of the green part? 2, yeah, 2. Okay, so we get 2 when x is greater than 3. What's the derivative in here? 0. Okay, so in the middle we're going to get 0. And what about the bottom? -2. Okay, now what about at x equals 3 and x equals -2? What can you tell me about the derivative at the boundaries there? Technically, it looks like it should be 0, right? But can we do that? Can we go from a slope of -2 instantaneously up to 0, instantaneously up to 2 at the boundaries? What's that going to look like? Sharp corners, right? When you get sudden transitions of the derivative like that, it always is going to look like something like this, right? Where it's got that sharp corner. And what do we know about sharp corners, of course? Undefined. Yeah, it's undefined. So the derivative is undefined here. So those are critical numbers, aren't they? Right? It's undefined at 3 and at -2. Does that make sense? Okay. I think there was. How would you draw the function? Well, in the derivative it would be, yeah. If we were to graph this thing, good question. What does this look like? If we were to graph the derivative function, let me just grab this. a sketch of the derivative function. Well, let's see, it's going to be when x is less than negative 2, it equals negative 2. So we get something like that, right? When x is between negative 2 and positive 3, it's 0. So it looks like that. And when x is greater than 3, it's positive 2. So it looks like that. And I have to have open circles at the endpoints because the derivative is undefined there. Right? Okay. Okay, there's a question. I'm going to do number 37, how about it? You guys can do 38. So 37 looks like this. We want to find, on our graphing calculators, we want to determine the absolute extreme of this function. Something like that, right? These are our domains. Okay, so here's how you can do this on a graphing calculator. You just go to y equals. You can graph a piecewise function by just putting the function piece in parentheses, and then right next to that you put the domain in parentheses. And then if you have, for every piece that you have, you can just add those pieces. So for this one, it would look like in parentheses, we're going to do 2x plus 2 in parentheses, and then right next to that, we need to put x is greater than or equal to 0 and less than or equal to 1, right? Okay, so here's how we do that. X, to get greater than or equal to, we go to the test menu, which is right behind math. So second test. And there's, on the test screen, there are two menus. The test menu has all of the inequalities. Okay. If you go over, scoot over to the right to the logic menu, that gives you, for us, really it's just, we're principally just going to use the and and the or. Okay. So we want to do x is greater than or equal to, so that's number 4. Greater than or equal to 0. And, so I go back to the test screen, scoot over to the logic menu, and x is less than or equal to 1. So test 6 is less than or equal to 1. And I put parentheses around it. And now watch, if I just go zoom 6, zoom standard, look what we get. See, it just graphs that one little piece between 0 and 1. Okay. Now we want to get the other piece on there. So you have an option here. You can either add it to y1 or you can put it in y2. I think there's a slight benefit to actually adding it to y1, and that is it treats it as a single function, and then it'll actually go, if you ask the calculator to find maxima and minima, it'll do that. It'll treat it as a single function. So we'll just go over to the end of what we already input in y1. And plus, now we'll put in the other piece. In parentheses, 4x squared. And then next to that in parentheses, we need x is greater than 1 and less than or equal to 3. So x, test menu greater than is 3. X is greater than 1. And let's go over to logic. X is less than or equal to, so 6. let's go ahead and graph this. Being as we're really only interested in the part that goes from 0 to 3, I'm going to go up to the window, and I'll go from -1 to 4, how about? So -1, oops, -1 to 4. And you remember how I can let the calculator choose the y value so it fills the screen? Zoom, what? Zoom fit, yeah, zoom 0. So I choose the x values, and then I hit zoom 0, and it'll calculate the y values for me. And so there's my piecewise function. How about that? Okay. Now I can use, I can do a couple things here. I can trace along this thing, but all the stuff I can do with a normal function, I can do with this piecewise function now, right? If I want to know, for example, what the value of that piecewise function is, even at the break. And this is kind of a boring one because they connect. But what if I had made that first one, how about, what if I had made that -2x plus 2? I'm going to do that real quick. So they don't connect. Okay, so now they don't connect. So if I ask the function, ask the calculator what the value of the function is at 1, it's pretty smart about it. So watch, if I go second calc value 1, or I could just do trace 1, I guess. Look what it does, it knows to put it on the first piece because that's including the 1, right? That's where x was less than or equal to 1. The bottom piece was only when x is greater than 1. Right, so it actually knows that. I think I can even ask it for a max and a min. If I go second calc, and it gives you the options of minimum and maximum. Let's ask it for a minimum. And left boundary, let's just make the left boundary 0. And the right boundary 3. And my guess, I'll make 1. And it tells me, look at that, it tells me the minimum is at 1, 0. That's the absolute minimum on that interval. And if I ask it for the absolute maximum, it's going to tell me right there. Okay? Does that make sense? So that's a pretty handy thing. It's amazing how much calculus you can actually do on these calculators. And I want you to know how to do it. You have to do it without the calculators too, obviously, but they're really good analytical tools. Okay. Any other questions? Anything that you can think, the stuff you're working on that's just, you feel like we need to spend a second on, maybe go through a practice problem. Okay? All right.